Good afternoon, everyone. Let's get started. So it's a pleasure to have Elias Most visiting us from Caltech. Elias received his PhD from the Yale University in Frankfurt in 2020. He then went on to Princeton University and the Institute for Advanced Studies as a joint postdoctoral fellow between the Princeton Center for Theoretical Science, the Gravity Initiative, and was a 5-year member of the Institute for Advanced Study. And then in 2023, Caltech snatched him, where he's been as a professor of theoretical physics. And Elias is an expert in computational physics. I would say made a name for himself primarily in numerical relativity, although he doesn't do just numerical relativity, general relativistic calculations. Expert in plasma physics, more like having one foot in plasma physics, one foot in nuclear physics, and a third foot in gravitational physics. Today he's gonna tell us about space-time and Turmoil.
All right. Thank you so much, Vasilis, and thanks everybody for coming. As Vasilis said, I'm trying to do this 3 foot, like one arm, I don't know, thing. So I'm going to try and motivate a little bit of like what we can do these days, studying compact object coalescence on like multiple scales, ranging from like stellar mass objects that we can see in LIGO to things we might be able to see with future space-based gravitational wave detection. And I also want to give you a little bit of a flavor of like how we do that in practice. Like what is sort of the, in a very nice pictorial way, the things that you have to do if you actually want to make images. Not like that, because that's just from ChatGPT. I can tell you what the prompt is, but I'm going to show you a little bit more in terms of what we do for the multi-physics model. And so here. The work that we do is not just work that I do, but it's really like a collaborative effort. Just going to mention some of these people throughout the talk, but that's currently what the group looks like. Some people have already moved on, others have just joined, and so there's always a lot happening. So if you're more interested, let me know afterwards. So if you think in terms of like compact objects, there's always ways that you can probe them in different forms. One of them, very characteristically, if you think just in terms of two black holes merging, is the emission of gravitational waves, part of the simulating extreme space-times collaboration between Caltech and other places, where the idea is, can you build very accurate waveform models that you can then use to interpret the LIGO observations of merging black holes, neutron stars, and more. But I'm not going to focus too much on the space-time aspects today. I'm going to show you more what happens on the sort of dynamics of a curved space-time, either when the objects are very close or when they're further away, or even sometimes when there's only one object to begin with. And so if you want to kind of see this talk in a more like global picture, then I'm going to start out with and tell you something about what we can do today. This really concerns stellar mass objects because that's what's in the LIGO band, what you can see. There's more than 200 gravitational wave detections with LIGO. I'll show you a little bit specifically what happens if a neutron star gets devoured by a black hole, or what happens when two neutron stars collide. And then I'm going to show you what we can do using all of the technology that goes into making these pictures, thinking about sort of the future, what can we do for supermassive black hole binaries or other systems that we can see with space-based gravitational wave detections. It'll be like 2 parts in some kind of interlude where I'm going to show you like how we do that simulation parts. And so one thing I want to highlight also is that ultimately what I'm going to show you is a simulation-based viewpoint. As I said, I really like doing computational work. And so the way you should see most of this talk is that there's a certain object you want to model, just like this artist over here. You make some sort of image, you adopt kind of a drawing style, and I'm going to show you exactly what the drawing style means later on in the context of what we discuss, say here for gamma ray burst. And then you make your own interpretation, and you hope that if you do multiple models and you compare them, there's some underlying kind of quintessence that you want to extract from that, the underlying physics that you want to probe. And so that's kind of the idea that I will adopt in this talk. Okay, we make lots of nice pictures, and we're going to learn something from. So I'm going to start out by first talking about the stellar mass case. So I'm going to talk about neutron star coalescence. That's what a neutron star looks like, and we're going to think about what happens when you have 2 of them and they begin to collide. And so I will focus mainly on like what the dynamics of the matter is in the system. And there's nuclear matter that's being present, there's plasma physics and strong magnetic fields being present. Those will be very important for some of the observables that we have in the system, specifically for binary neutron star coalescence. And then I'll also tell you how some of those concepts, especially from plasma physics, carry over if you think in terms of things around neutron stars with very strong magnetic fields like magnetars or ultimately black holes. All right. I wanted to give you, before we start, at least I think most people maybe know what a neutron star is, but maybe not everyone. And so I tell you my personal view of what a neutron star should be, or at least the questions that we can ask about it in the context of this talk. If you look outside, you have very nice mountains. We have them too in LA. This is where Caltech is where this little sort of arrow is pointed. And if you ask what is a neutron star sort of on our local sort of horizon, that's what it would look like roughly in size. So it's an object with about 10 kilometers or so in radius. It might not really look very yellow overall. If you ask, what object should I compare this with, at least in mass from a point of view of gravity, roughly with the sun, because it's roughly the same mass, maybe a little bit more massive, but not much more massive than twice the mass of the sun. But then when I sit very close to it, maybe I get a sunburn or it's really unhealthy, but that's actually not what I would see. What I would see would ultimately a pattern such as this one. It's actually a simulation image where you try to solve the shallow water equations on top of a millisecond neutron star, pulsar. You can actually then see, you have some, formation of jet streams, you have these little vortices. It looks a little bit like Jupiter in the IR. And so many of the concepts that, you learn from other fields carry over to the system as well, just in a very, very extreme form, because this layer where you see sort of this fluid motion is maybe on the order of less than a meter in height. So it's a really, really extreme object. Okay, so why is gravity important? We heard a lot about relativity in this context, gravitational waves. The main reason is if you look at any such object, you can compute one number. The number is like an Einsteinness of an object. It's not called like that, it's called compactness. But really, if you add in another m in there, it's basically a comparison of the gravitational self-energy compared to its rest mass energy, mc squared. Okay, and you can compute this number for different celestial bodies. For example, for the Earth, it's 10 to the minus 11. So of course, if we communicate with satellites or we want to use our navigation devices, relativistic effects become important. But otherwise, for day-to-day life, maybe not so much, because the number is very, very small. This is really for general relativistic effects. But the sun is 10 to the minus 6, so maybe a little bit, but not really too much. And then if you look at black holes, it's like the most extreme version of this family. The number is 0.5, so it's kind of the upper limit that you can go to. When we talk about neutron stars, why we need gravity is because this number for a neutron star is roughly in the same order. And it's really just a statement of the fact that you take the mass of the sun and you put that in an object of 20 kilometers in diameter. Okay, it's just a really, really extreme object where all of those fundamental physics comes at play in unison. And just for comparison, how small this thing actually is, if you compare it to the Earth, it's really, really tiny. But that's what we want. Okay, and then what these neutron stars can do here, for example, you have a double pulsar system. They orbit around, they emit gravitational radiation. But not just that, they also have very strong electromagnetic fields. Neutron stars are potentially the strongest magnets in the universe. And because they can do that, they can have secondary emission processes. And we're going to see some of that later in the talk, meaning that we can't just only see them in gravitational waves, but also in this case in radio. And then you can try and put constraints on the properties of space-time just by travel delays of the radio pulses in the system. So what we're going to do here is, then in some sense, we have to solve the equations of Einstein, but we also need all the extra degrees of freedom, all the extra ingredients for the matter around it. We need the nuclear physics, the plasma physics, and so on. And that will be something that will come up in various forms and ways throughout this talk. But the biggest challenge is that if we want to do this, then Einstein's equations are very complicated. So you cannot just be like Einstein, go to the board and try to solve that. You have a local expert here, Vasilis, also does that on a daily basis. You really need to do that numerically. You need to integrate those equations on computers. And so think of numerical relativity or computational astrophysics, more broadly speaking, as it has a lab. It's usually in the basement or in some outside facility where you have supercomputers. That's the one at Caltech, at least before they moved the server rooms. And then you can say, okay, I put these equations on these computers. And the interesting and important point, which I'll highlight towards the end of this talk, there has been a revolution ongoing in the field because the computing power for these types of simulations has massively advanced and ramped up over the years. The fundamental word is exascale computing. That's 10 to the 8 flops, floating point operations per second. That's all the computing that powers, your ChatGPT query. Okay, and you can use that also for science and research, and you can specifically use that to solve Einstein's equations with all the equations in curved space-time. And I can show you if you use those machines, which allow us to run simulations that are maybe bigger by a factor of 10 to 100 than what we could do before, there's interesting problems that we weren't able to tackle, but now we are. And so there's really a lot of exciting opportunity coming along the way. Okay, so now I showed you roughly what we're studying, what object, how we will do it using some big computers. I really also have to tell you kind of what equations do we solve. This will be the first version of that. There will be second version later in the talk where I show you kind of more pictorially what kind of approximations we have to take. But for now, we will put some version of general relativity in there because we want gravitational wave emission. Maybe we want dynamical black hole formation. There's many things that we need that for. So we need to solve those equations. We need some description of the matter as well, meaning that, for example, the neutron star or a black hole accretion flow, or even if you think of it like a magnetosphere, we'll need some version to describe the dynamics. Here we'll adopt largely a hydrodynamical type approach, but that cannot just only model water. If you actually tell it what nuclear matter is using some closure relations for the equation of state, you can also model the dynamics of dense matter. That's very important ultimately if you want to make connections both with gravitational wave signals that have been detected, but also with electromagnetic observables from the nuclear matter that has been ejected from the system. If you want to study non-thermal emission, you need to also even understand what the secular evolution of the system is. You need to solve some form of Maxwell's equation. So you need to put that into the mix as well. And ideally, because you have nuclear matter, you also need to put in weak interactions for your neutrino physics. And so if you take a close look, you basically now have all strong forces of nature in their dynamically important regime combined in the system, meaning we really have to solve a lot of equations. They're very complicated. We will need to make approximations. And depending on what we do, we'll get different answers. Okay. But for the moment, let's just say we can do this. We have these computers, we have the equations, and we know how to do it. So this is an animation of a merging neutron star binary. It's very close to merger, about 15 milliseconds in real time. You can see here kind of in slow motion as they orbit around, they emit gravitational waves. You can't really see that, but what you can see is that over time, they get closer and closer together. And then ultimately, those two neutron stars will collide. As they collide, there's a lot of debris that's flying out. You can see this right now. They smash into each other. There's a lot of stuff flying out. This matter will turn out to be very neutron rich. Ultimately, that can then power things like kilonova emission as the neutrons undergo upprocess nucleosynthesis. But for the moment, this hot remnant just rotates around, emits more gravitational radiation, and then succumbs to the pull of gravity and forms a black hole. Then the simulation stops, but you can actually push it further now, and you can ask, okay, what happens with all the matter around the black hole? And then you're in a very generic question of what happens if you, say, have jet launching from the system, if you have magnetically driven winds, and all of those things. So I want to give you some flavor of the questions that people have been asking in this context by basically going through some of the stages in the movie that we've seen. And then I'll give you some outlook of the things that we haven't seen yet, but we're interested in understanding as well. So this in-spiral part is very interesting for gravitational wave astrophysics because that's something that's very regularly detected in the case of binary black holes. There's also been detections of black hole neutron star mergers. I'll tell you a little bit more about them later on. They're somewhat special in terms of the parameter range that they lie in, but there's been one very important binary neutron star merger, which I'll tell you a little bit more about, which was accompanied by very interesting science and also observations in the optical, IR, radio, and gamma rays, so almost across the entire available spectrum, meaning that in the neutron star in spiral in the gravitational waveform, which you kind of see a little bit over here for this event in 2017, you actually do got an imprint of the squishiness of the neutron star. There's been actually great work that was done here a while ago by Karen Raythel, Fayal Uzel, and others, where then you can learn about how big the star is, and what does it tell you then about nuclear matter? So that's something, if we get more detections, we can definitely learn more about, and especially with facilities in next generation, meaning next decade, there's more to learn. There's also been a lot of great work about what happens when you actually have the collision itself. You should think of the neutron star merger as like smashing two big blobs of nuclear space goo. If you do that, you end up in collider-like conditions. There's been a lot of work on that as well. By me, others, Karen Raythel and Vasilis also did very good work on that too. What happens when you actually have finite temperature corrections to the system. And then you can really probe conditions of nuclear matter that otherwise are very, very hard to explore in laboratory facilities. You can ask me after the talk what exactly that means, but in practice, there's stuff we can in principle learn from that, specifically with facilities like Cosmic Explorer or Einstein Telescope. Now, the challenge is, and this goes back to the point of what physics goes into the system, this turns out to be a really, really high problem. And the problem is if you say you have two gravitational wave signals where now this part has not been detected yet because it's outside of the gravitational wave band, though, for example, at Caltech, we have one gravitational wave experimental person Lee McCullough, who's trying to build a device for doing just that. If you can do like minimal photon detection for trying to see if you can get constraints from the difference in the post-merger, then the challenge is, what does it tell you? Well, maybe it tells you something about quark deconfinement. There's even models about dark matter potentially. There are models of finite temperature composition in part worked out here, which I think are very interesting because that's matter that you cannot get from pulsar timing if you want to do constraints from those systems. There will be a lot about magnetic fields. I'm going to show you a little bit more about what that means. And then maybe you also have effects from neutrinos. There's been a lot of work and effort in the community on that recently. I won't talk about this, but basically you should think of this as even a chemistry lab for neutrino interactions, basically converting neutrons into protons and back. And then if your equilibrium chemistry pans out in interesting ways, maybe you can detect that too. So there's a lot of physics at play, very complicated, all in unison. And the question is, how do you disentangle that ultimately? And this is where you need simulations and fiducial models. Okay, so now you could ask reasonably, given all the complications and all the, all the potential challenges that you might have to simulate, that what do we actually know? And there's one big thing I want to highlight, what numerical relativity with neutron stars has delivered, the very robust prediction, namely, if you have the collision of two neutron stars and they're very massive, in principle, they can be so massive that the resulting merger remnant cannot support itself against the pull of gravity, forming a black hole. In that case, when does that transition happen? And that's something where many groups around the world have spent the equivalent of a few $1 million trying to answer that question. And that's actually robust prediction that has been delivered. Here's one that includes spin as well. And the interesting thing is, if you can do that and understand that, you can interpret events like 1904-25, which was an event of very massive merging neutron stars. It was not accompanied by any electromagnetic counterparts. And then having this kind of insight, when or when not you form a direct black hole, where in this case, you did form the black hole relatively directly, helps you understand why you're not seeing what otherwise you would expect to be seeing. Okay, so it's really something where numerical relativity has really delivered. And so that brings us to the main part of this talk as well, that really, doing those things in dynamical space-time is not just about dynamical space-time, it's about the stuff that happens in it. Meaning there's a lot of electromagnetic emission potentially, both from the neutron-rich matter that got ejected, also from the accompanying electromagnetic field that goes by the multi-messenger picture of the system. Not just of that system, I'm going to show you also what that means for merging black holes and other objects, but really there's an interesting thing to be learned here about that in general. And there are two main things that have been discovered for the 1708-17 event, one being the kilonova and the X-ray afterglow. The main idea there being, for the kilonova, you eject a lot of neutron-rich matter. That's an observation that was done at Caltech by my colleague Manzi Kaslival, where you can actually see, and there was a recent one, by the way, that was contested, but there was one in August as well for potentially subsolar mass event. Where what you see is the ejection of very neutron-rich matter. Those, on the timescale of a day or so, our process nucleosynthesis takes place. The heat of that powers a transient that becomes transparent on the timescale. Then you see a rise in your light curve and a fall that's relatively rapid. That's something people have been looking for, that explains in part why we get production of heavy elements in some systems at least. And so there's interesting ways for numerical activity to tell you how you form that. Here's a picture of how you can see this. This is like an animation that shows you all of the, basically, the same movie as in the beginning, but now you color code which of the neutron-rich matter makes it out to infinity and which one doesn't. So you can see this here in green. Basically, those are all the matter particles that makes it out. And then the red ones are the ones that fall back. So you can really kind of make predictions for, how much mass gets ejected on what time scale, what's the physical mechanism driving that, and can that tell us about changing in the kilonova, can it tell us about spectral evolution and so on. There's interesting things one can ask there, and where simulations are now able to produce reliable predictions for that scenario. Similarly, there has been the observation of gamma ray burst, actually the first one coincidentally, associated with a neutron star merger, about 2 seconds after that one. It was a bit low in luminosity, and there's various ways of why that could have been, including just seeing the relativistic jet that was launched off axis. But the interesting thing is, given that you have this connection, we can actually ask multiple questions about that. Namely, do all neutron star mergers do this? If they don't do that, what's the delay time? It's always 2 seconds. Or may some of them not even launch a jet at all? And those questions really help us understanding some of the physics that's going on, in particular the nuclear physics, but also the physics of strong magnetic fields. I give you some toy animation for what that looks like, and then I'm showing you more of how that ties to the merger. So if you want kind of the basic picture, you have a black hole here, you have a finite mass disk over there, that's the density, that's the Lorentz factor, and then there's some fancy numerical grid structure. That's also there. Let me see. right over here. And so as the matter gets accreted on the black hole, you can, in some cases, have basically extraction of black hole spin. Actually, for that system, that's not always the case, but you can have magnetocentrifugal launching. And then you basically get an acceleration of the material outwards. You can see that the Lorentz factor begins to increase. And that then can ultimately accelerate further, reaching Lorentz factors of maybe 50 to 100, powering the gamma ray burst under certain conditions. Okay, and as you can see from the technology that's going on, that's very complicated with dynamical grids in spherical symmetry, not spherical symmetry, spherical geometry. That really allows us to kind of track and model these systems very accurately and try to understand really what are the conditions for launching, what do the magnetic fields do in this case, and so on. That's one of the big questions that people have been trying to answer. One thing that I want to highlight is that, understanding this question is a little bit separate from, let's say, understanding how AGNs power jet-like outflows. That's a study we did for the AGN case. This is to date the largest simulation where you kind of keep throwing mass onto the black hole at separations of 10 to the 4 times the black hole size. This is really challenging because for this kind of large, what's called Bondi radius, the integration time is really, really long. It's kind of almost 10 million times the dynamical time scale of the black hole. But you can really see that you have an almost infinite reservoir of mass. You keep just feeding the black hole. At some point, you look at the jet, and likely you will see it either in some sort of equilibrium configuration, or for some of these objects, if they're real, like compact symmetric objects, you might see something that's stalling, and then maybe it's restarting again. But in either case, it's kind of not sort of determined by having a finite mass reservoir as the neutron star merger case has. So in the neutron star merger case, really important to understand what's the jet launching time, rather what are kind of the overall properties of the jet in this sense. And that ties into physics of the accretion disk. Physics we see in other contexts, for example, in the sun, in the solar cycle, that there are mechanisms that allow us to generate very strong and dynamically important magnetic field in systems that usually start out either with weak magnetic field or that have like cycles like the sun that can change their polarity, where you have like phases of strong solar activity that the polarity of the field switches and so on. And accretion disks around black holes do the same. There's a similar dynamo operating, maybe not as similar to the sun, although there have been proposals about having magnetorotational and stability-driven dynamos in the outer layers. But in any case, there are processes in the accretion disk that allow you to amplify the magnetic field, ultimately bring that on the black hole, and then launch an outflow. But there's a certain time scale or time lag that it takes to do these simulations. And the nice thing is that these exascale GPU-based simulations have allowed us to actually push this frontier quite a bit as a community. So one other thing why this is really a challenge in the merger itself is that many of the magnetic field dynamics, really, if you think in terms of the magnetic field causing sort of the collapse to the black hole in some cases because it removes angular momentum from the system, the magnetic fields cause outflow and many other things. If they want to do this, they have to reach a certain strength. If you look at the neutron stars that you merge initially, and you just look at the pulsar population, the magnetic fields are really, really weak. They're far too weak to do this. If you just do a simple estimate of like what's the dynamically important field strength value at the core of the neutron star, that's 10 to the 18 Gauss, at the surface is 10 to the 16 Gauss. If you want to launch any outflow from the star magnetically, unless you reach 10 to 16 Gauss, you're out of luck, nothing will happen. That means that there must be some process in the merger that amplifies the magnetic field to reach sort of the required strength to enable that. So there's a dynamo process, maybe not exactly the same as in the sun, but in spirit, very similar. And there have been a lot of works in the community over the past even 20 years, going back to 2005, looking at that. For example, there are small-scale dynamos, meaning that at the merger, you develop a shear layer interface, you get small-scale dynamo amplification, the field will rearrange itself inside the merger remnant, and it will then be further amplified using a large-scale dynamo, so that ultimately you reach conditions that explain why you see what you see in terms of some of the observables.
Can I ask a question? That went pretty fast for me. The magnetic field. So where does 10 to the 16 come from? You said
if you look at the magnetic energy density and compare it to the rest mass energy density, right? That's what you would ultimately need if you want to launch an unbound outflow from the surface. Then that number is 10 to the 16 Gauss at the surface of a neutron star. So unless
why would a magnetic field ever launch anything? I mean, it doesn't launch. I'm confused.
Well, I'm going to show that in 2 slides. I'm going to show you, you have a magnetically pressure-driven outflow, or you have a magnetocentrifugally driven outflow. There's 2 mechanisms in which, a gradient in magnetic fields can launch outflows. I'll show that in a second. You'll see. So let's say you reach those conditions, then, can you launch a jet or can you not launch a jet? And there have been many works, including some by Basilis here, going back to 2015, that's basically saying that, maybe these systems actually can launch very strong jets, either because the magnetic field initially is strong or because something has to be amplified. And the interesting shift that's happening in the community is that initially we thought, okay, it always has to be a black hole, because for black holes, we know how to make jets. And maybe for stars, it's a bit harder. There are sort of what's called magnetic tower solutions. But as of maybe 2 years ago, we have a good understanding for how this works in the stellar remnant as well, meaning that we can now even explain or try to explain some of the dynamics of these outflows that are magnetically pressure driven from the remnant. There was additional credibility, or like, let's say not credibility, but let's say motivation. There were people who claimed that they found quasi-periodic oscillations in archival gamma rays, burst data that was specifically time tagged, showing that those, quasi-periodic oscillations maybe are associated with the oscillations of the remnant. Whatever you think of this is a different story, but let's say we can take it as a motivation to ask, if you have an oscillating star at the base of this jet, what would that do? And, is there some constraints that we can put? And really another thing I want to highlight there is that numerical relativity overall has come a long way in kind of now understanding what exactly happens after the merger. What kind of dynamo process is at play? It's a large-scale dynamo. The simulation down there by Kenta Kiyuchi was one of the most expensive ones done in the field ever. And they really showed that you have a large-scale alpha-omega dynamo happening that can amplify the magnetic field very strongly, so that the field ultimately breaks out, forms these sort of helical structures, and then launch an outflow from the star. There's many different works, including some that I've done, some that others have done, kind of coming exactly to the same conclusion. So really, we have a good understanding now that that's how it should work. And to come back to Sam's question, there's basically two ways of how you get the field out. The first insight from this is, if you have very, very strong field that's sort of wrapped around on the inside of the star, this field is ultimately unstable. That goes by the name of Parker instability. It's a similar process that happens in the solar corona when kind of these magnetic flux loops break out of the sun. Same thing happens in a neutron star as well, and we were able to show this for the first time that happens. And then this magnetic field gets ejected outwards. It forms this tower-like geometry and can then cause an outflow along this tower, which is shown here. So here at the base is a star. There is this very helical structure that sort of pushes things out like a spring. That's the picture you should have. There's basically a gradient. And then we will also be able to show for the first time that it's not just the pressure gradient that drives an outflow. There's a substantial, about 30% contribution coming from something that's called Blandford-Payne mechanism. It's magnetically centrifugally driven from field lines that just stick out here in the star and the accretion disk. And then you can also centrifugally launch stuff. It's basically like you fling it out, ultimately the stuff decouples and then flies out. Quantify that and show that for the first time also recently. So the system seems very complicated in launching magnetically driven winds, but now we have kind of the tools and the understanding to really tackle this problem and then make more robust predictions.
Since you were answering my question. Okay. So I like that you're saying we have the understanding. I'm not there yet, just from, this is not a criticism, just so by Blandford-Payne, I got that. Particles are stuck to field lines. Exactly. Field lines are rotating. Exactly. They fly out. That's
then
cool.
The decouple once you reach
an outflow. But I'm missing the similarly simple explanation for why, like a coronal flux, like a little loop on the sun. You said you found something analogous to the little
loop,
flux
basically,
loop
so
that launches an outflow. So
no, what you have two things here. The first one is you have the magnetic field close to the surface. This field is unstable. There's a gradient going out. So the field line will ultimately push itself outwards.
I'm okay with that, but then why was this spring, and how are you going to get a giant jet from? I mean, we don't see jets from the sun, right?
No, I mean, the sun cannot get the collimation, but the neutron star. So basically what happens in a neutron star is that you get a coherent structure of a magnetic tower, which is like a large helix. And then the helix has a net pressure gradient. So there's like a grad P term from the magnetic field, and that's pushing stuff outwards.
I don't know. It just seems hard to understand where all this energy is. Yeah, sometimes that'd be great.
Yeah. The simplest explanation you can think of is it's kind of like the Bernoulli equation.
Yeah, exactly.
If you
Like
just take
forcing it through a tiny nozzle.
Yes, exactly.
Yeah.
So it's really,
well, if that's it, you should say that.
that's what it is. It's really magnetic pressure, and then rho times B. Magnetic pressure drives the flow out. It goes out, the magnetic field goes down, and you get the acceleration. That's really.
Okay.
Which gives you a
see why you need a big field for that.
Exactly. You need a very big field because the Bernoulli criterion is basically rest mass energy density plus magnetic energy density. So if that's not substantial, then you're not going to get any conversion from it. So I'll talk about it later. But yeah, those are the two mechanisms. And then the main thing that sort of have enabled progress in this area is basically being able to connect the theoretical models and our understanding using computational tools. Basically go from the left to the right using a simulation at the center. And then the important thing is that you can't do that by solving those equations on the right exactly. They're too complicated for that. But we have to make approximations, and how we make these approximations turns out to be important. Okay. So I'm not going to show you what these equations or approximations look like, but I'm going to show you using this very nice visualization what they sort of do if your question is, this is reality, that's what you want to model, this painting, and you want to reproduce that using some of the assumptions that we do in computer simulations. For example, hydrodynamics, we have magnetic fields, and then there are other things that I will tell you about what they do. And you can ask, okay, what actually are the aspects that we're losing out on, and what are the things that we gain? Because as you can see, not all of these things will probably be the same computational cost, and they cannot model all of the aspects at the same time that we want to understand. So if you look at this image, it has like mountains in the background, it has a river on the right, it has people dancing in the foreground. The problem is really hard because it has an intrinsic separation of scales. The people are very small and the mountains are very big. That's a common theme in astrophysics. You can think of going from the outer galactic scales to the galactic nucleus, say, or going from like the star to the microphysics in the stellar plasma that then dominate the dynamics. You can't solve all of that at once. You need effective models. And then each of these kind of recreations of that image is an effective model. You can do quick and dirty, like just hydrodynamics, but you can see that there are many things that you don't spot. There's no river there, there's no people, there's no house that they're dancing on, so it's really not very good, but it's quick and easy. So if you want to have like a very simple picture, you would do that. If you do magnetic fields, say, included, and they're important in your problem, you capture at least some of the layout of the land, but the things you don't get. And what you don't get, for example, in this case is color, and color here represents the electron physics, the emission physics. And so these processes with MHD can fundamentally not capture. If you do force-free electrodynamics, like I think Sam does recently, has done a little while ago as well, you get false color, but you can capture some of the things in a brutalistic way, as you can see there. Or you can do like full fidelity, all color, but you lose out the ability to distinguish small scales from large scales, like the people are as big as the mountains. So depending on what you want to model, you need to make approximations. You need to make assumptions that depending on what you pick, you can study certain aspects and others you can't. And in all the things I was showing you, we had to make similar simplifications, mainly in this regime. But I'm also going to show you in this talk things from these other regimes, which can show you similar things. And then there are even questions on top of that, namely, even if you can do all of that, how well can the computer actually reproduce any of these images that you want it to reproduce? So there's intrinsic challenge. But the nice thing is you can basically apply those technologies to different systems. You can apply them to magnetar flares. You can apply them to relativistic jets. You can apply them to, EHT plasma physics. You can ask what's actually causing the emission. And what you should have learned, for example, that this simulation over here does not include any of that. So the color has to be added in by hand, in particular for those simulations. Or you can do this for gravitational waves. Where the gravitational wave case is very special because in gravitational waves, there's no approximation to be made. If you believe that Einstein's theory is right, you have to capture all scales, meaning the horizon scale. And if you don't do that, you'll not get a fiducial value or fiducial solution. So there is no approximation, but then you need special numerical techniques. For example, you need to think about, how do you accurately draw using spectral methods, for example, that give you very high order convergence, meaning very, very little cost for probably the best gravitational waveforms. This is what the SXS collaborations do. And then finally, just to quickly highlight this, although I will not say much more, you can even say, okay, maybe gravity should be thought of in similar ways. And you can even do this. You can also interpret gravity in some of the forms that I've been showing in terms of electrodynamics. If you have questions, you can ask me later on. Okay. So I want to give you a few examples for why it matters, meaning I will show you two predictions that people have made using different approximations for the same problem, finding different outcomes. And then the question is, which one is right? And the answer will be, it depends. And so we look at the simplest case within sort of the toolbox that we have, namely what happens if a neutron star collapses under its own weight into a black hole. We've seen that can naturally happen after neutron star merger. It can happen from spin down of a neutron star that's rotationally supported. So maybe we can just do that. Say in the merger, this can in principle last up to 1 day, but depends very strongly on the merger parameters and the equations. So if the neutron star, just like a pulsar, has external magnetic hair, in principle, this hair will also go on the black hole. And there has been a huge amount of work showing that, both analytically, but also numerically, black holes can't keep their hair. They have to bald. They have to lose it, just like me. Okay, so you have to lose hair at some point. So what happens in this case is that the question, like, on what time scale does the black hole lose its hair? And is there any observable transient from when that happens? And that has been invoked in multiple contexts. For example, people have thought, okay, if I do like a force-free like simulation, so if I pick this sort of false color image, I get a solution that looks like the one over there on the right. And people have thought maybe that gives you radio emission. Or people have said, okay, if I take my best most fiducial model, which is maybe not good for global scale, so I cannot tell you what happens in large distances, but it can tell me what happens close to the black hole horizon under some assumptions of what scales mean in this case, and you can ask me that as well. And you find very different pictures in the bottom part. You would say maybe it's an X-ray transit. And so depending on kind of what physics you put, the question is which one is right, which telescope should I use to observe this phenomenon? The answer turns out that depending on what you do, both of them might not be correct. The reason we thought about this in part is this one, but I will not talk about those two claimed detections because I think both of them are not correct. But basically, there's motivation for why a collapsing neutron star might give you some form of transient, for example, in the radio band. And then the question is, okay, what from the physics picture we can actually associate with the collapse itself? And so the challenge in that seems not to be in the kind of formation of the black hole. The challenge is the propagation of the waves. So even if you start off with this kind of solution, which looks like very nice electromagnetic waves that are going out, as they propagate, there's a nonlinear effect in the magnetosphere in the background of the neutron star, which graphically looks a lot like a wave coming ashore. So if you do a trip to the seaside and you see a wave that's making its way onto the beach, then basically the bottom of the ocean is rising, meaning the wave is steepening. And at some point, the wave will break, and you generate such a scenario where if you surf right here, you get sucked in, and the wave will break all around. And what people have realized about 2 years ago in the context of neutron star magnetospheres, those waves behave exactly in that way. Which turns out for some of these waves to be a big problem if you want to explain how FRB-like radio emission can be produced close to the star. But the physical process is really something very similar to that one. And so what we did, we performed the first such simulation where we actually were able to correctly capture this formation of the shock in the collapse of the neutron star. So basically, we're saying that both of these approximations and predictions were wrong, because if you think about the physics that you're missing, which here is MHD physics, you form what's known as a monster shock, potentially the strongest shock in the universe, because it locally can reach under those conditions Lorentz factors of 10 to the 8. And you can see this here if you look at the temperature and the Lorentz factor. There's basically, as these waves propagate out, the black hole here now, the newly formed black hole will be at the center, you form something that's strongly heating and fast accelerating. That's exactly this monster shock-like solution. And if you compare it with the analytical derivation from Andrei Beloborodov, it actually matches very nice in shape. So we could really show that that's what should happen. And then you have dissipation of energy inside the shock, which actually in this case should produce gamma rays if you run the realistic numbers. So we made a prediction that maybe there should be a millisecond-like gamma ray transient. And there's one claim recently in the literature that thing may exist. So there was a reanalysis of GBM data that may or may not have found a millisecond transient at very, very high spectral energies. You can ask me about that as well. But I think it's an interesting kind of insight to say if you do the physics right, you arrive at a better conclusion. We even showed that if you run this further through the formation of the black hole, that you can have imprints of the black hole ring down on the electric and magnetic fields. And then you can hypothesize things such as, do they actually get imprinted in a gamma ray burst? Does it have anything to do with these clade quasi-periodic oscillations that have been found in 2 archival gamma ray bursts? But it's an interesting thing that we can make those simulations and really try to understand what's happening and what predictions we can make to make that more robust. So going from kind of using this tool set on neutron star coalescence, I want to give you one brief example also what we can do for a neutron star black hole. The reason why neutron star black hole is interesting is because those are the sources that LIGO has been seeing involving neutron stars. And they are so special in a way that the black hole in those sources is usually 5 times larger than the neutron star, in which case the neutron star just gets swallowed whole. There's no matter around. There's no upright node, no kilonova, no jet launching, nothing. It just goes in and that's it. Okay, so maybe there's nothing to be expected. The gravitational waveform immediately shuts off, which it will do anyway, but you cannot have any of these other multi-messenger signatures. But what you can have is if the neutron star has a magnetic field, as I just showed you, maybe there's a new type of transient that people can...
Sorry, very simple question, what you just said. You're capable of getting the neutron star in there without any tidal disruption?
Yeah, basically the disruption depends on where the disruption radius is versus where the inner stable circular orbit is, right? If basically the inner circular stable orbit happens after you have disruption, so further out, so then nothing can circularize, everything will go in, right? And that depends on the mass ratio. So for those sources, it happens that if the black hole is about 5 solar masses and has sort of moderate spins, you kind of at the edge, but if it gets more massive, it will just eat it whole. Because disruption happens too late in the source. I'll see it that way.
So the neutron star is able to get that close, the tidal disruption doesn't even take place.
Well, it does get sort of a little bit stretched, but then it goes in before it can go on a stable circular orbit, right? Because it just happens to live. So what that means is then there's no way of just getting any mass ejection, but maybe if the neutron star has a magnetic field, there are ways to find transients. And the reason why this is interesting is because at Caltech there's actually an observational program to look for these things. So there's the Owens Valley Radio Observatory Long Wavelength Array that's more than 200 kind of coat hanger like antennas in the Owens Valley. That was PI is Greg Hallinan, and his student Nikita Kozogorev has now put a pipeline in place that they can actually buffer all sky radio data for about 10 minutes after a merger event. And that pipeline is in place. It's operating as of a few months ago. And the nice thing is because of the frequencies which it operates in, which is below 100 megahertz, the travel time delay is such that even with current sort of early warnings from LIGO, you can still get enough from the wave signal. They demonstrated that for a recent neutron star black hole merger earlier this year. So the whole pipeline is operating and people are looking for what's happening. There's also a proposed search for looking at CHIME FRB data to see is there any correlation. So far, the answer is no, but the search is ongoing. And then there will be a new radio instrument, DSA 2000, who many other things that it will do, will also continue to search for LIGO follow-up, also for all of the associated jet physics. And so the question you might ask is, why would you, even expect that there should be any radio emission? And the interesting thing is, up until maybe last year, the answer would have been maybe it's hard to get. But now we have two galactic sources, not consisting of neutron stars, but consisting of white dwarfs and red dwarfs that have exactly the phenomenon that we're looking for. So we can have like a galactic mimic system. So let me say something quickly about that. Those systems consist of white dwarf M dwarfs. They've been detected as what's called long-period radio transients. These are radio transients with periods up to 2 to 3 hours. And there are two sources that are spectroscopically confirmed to be white dwarf hosting. So we really have direct confirmation that the source, which basically produces a radio flash once per orbit, is really powered by a white dwarf. That raises a lot of questions because white dwarfs on their own cannot produce radio emission, but they are known in binaries with M dwarfs to do. For example, there's like the ARSCO white dwarf pulsar. And so the interesting question is, how did they do that? And does it tell us anything about the neutron star case as well? And so what we did together with a postdoc at the Jean, we actually worked out a model and also a simulation-based model for understanding how does the radio emission in the system work. And the interesting thing is there is sort of a very close by analog of that source, which we think is how it operates, namely the Jupiter Io system. So in Jupiter, you get decametric radio emission from the motion of Io in its magnetosphere. You can kind of see here, this is Io, this is Jupiter. That's a Juno mission. Here you see the connected flux tube, and you can kind of see that the radio emission varies with the motion of Io, and that's associated with the electron current in the flux tube. And we also know that the mechanism for this is called the electron-cyclotron maser instability. So we even understand exactly how that works. And so what we showed recently using very advanced simulations from the board, so that was the kind of the colorful picture I was showing earlier, where we have this sort of, we get the scales wrong, but we get all the colors right. So we did that kind of simulation, trying to understand if the same mechanism that operates in Jupiter can also operate on a white dwarf. And the answer is affirmative. So those are simulations where you could think of the electrons are coming from the left, the magnetic field is going in this direction, and then the same kind of maser instability takes place under white dwarf conditions, producing coherent radio waves that propagate out and away. And if you use an exoplanet visibility model, where you can even, because the visibility of this is very strongly constrained by the geometry, you can even see that you can only see it once per orbit. So everything nicely pans out. Even the polarization looks good. There's some constraints on that within the limits of what we can simulate, but it's really interesting. And to highlight why we need to do those simulations over analytic estimates, what people have done maybe 50 years ago, is if you actually do the simulation, you solve the full thing nonlinearly, you find that the nonlinear stage is 10 times more efficient in producing radio emission than expected, which helps a lot explaining why the luminosity of the sources is what we see. So really simulations can help in those contexts as well. So now that we understand that this can happen, what we expect to see for our neutron star binary. So if, let's say, with the Owens Valley long wavelength array, we keep seeing something, what could it be? It could either be powered by the orbital motion, just like in the case of this white dwarf and this M dwarf. It could be powered by gravitational interaction. We give tidal forces shattering the crust of the neutron star. Think of the neutron star as a hard-boiled egg. It has a shell. You can crack the shell, and maybe that couples somehow to the surrounding magnetosphere. Or you could have, the collapse-like transients that we have already seen. And the nice thing is, using the tools that I was showing earlier, there's been a lot of work in the community actually modeling all these different transients, both for isolated magnetars, but also for the binary cases. So we can really make very detailed predictions for what we would see, what mechanism operates, and what band this would be in. So I want to show you, in the context of what we've seen, two examples of that. Interesting predictions and an interesting finding that we did not anticipate. So for example, in this case where the neutron star gets swallowed whole, we can ask the same question as before. Neutron star goes in the black hole, some transient happens, but what would that be? I already showed you that we demonstrated this will likely lead to monster shock formation, and we were also able to show that neutron star black hole systems do that too. So there is a monster shock, the energetics are slightly different, and in the regime where the shock operates, this will give you radio transient. But we found something else, something we did not expect to see. This was work led by who was a grad student, now moved on to Princeton. Namely that as the black hole transition, as the magnetic field transitions on the black hole, the magnetic hair doesn't get lost immediately. In fact, what happens is the magnetic hair spins around on the black hole, which almost looks like a pulsar wind. Over here, this is the current sheet. This is a specific kind of cut to the plate, meaning that over the course of a fraction of a second, this thing produces a strong pair wind. And if you run the estimates of like the effective compactness of this wind, you expect that basically you're so copiously pair producing that ultimately those pairs will recombine as it becomes optically thin and produce an X-ray burst. So there's even a nice prediction for what the system could do, but also very nice physics because this black hole pulsar state was hypothesized but never shown to actually form. We were able, using full numerical relativity plus the correct treatment of the magnetic fields, to show that this really can happen.
How long does that last?
That will last for about 100 milliseconds or so. It decays exponentially afterwards. All right. And then there's another thing that has been associated. This was motivated by detections of precursors to long gamma ray bursts already a while ago. It was actually led by postdocs at Caltech at the time, Dave Tsang, where they said if you tidally shatter the crust of a neutron star, in principle, you should also be able to see this. And they were hypothesizing that maybe this gives you gamma rays. This kind of the picture that they made, there's tidal interaction. You're just like a glass, the high-pitched voice, you shatter that, and then you learn something about how the crust was shattered. This is not a picture I would put because this is, I think, what will happen to the neutron star if this actually happens. Like it's really kind of a doomsday event. But the big question is, based on all the tools and all the insights we've seen, can we actually make a more robust prediction using simulations of what we would expect to be seeing in this case? And so the answer is, again, we can do this. This was one of our first applications of the new exascale capabilities computationally, because it's really, really hard. You have to look at nonlinear wave propagation in the context of a binary where you both have the black hole horizon and all these waves propagating out. But we were able to show that basically these waves nonlinearly steepen into blast waves. They rip open part of the magnetosphere, propagate out, and then probably interact with the wind, similar to FRB models that have been made for the galactic magnetars. So we think the system will not produce gamma rays, but maybe it will produce FRB-like transients based on the physics modeling that we can do. It's really cool because we get the scale separation right. We see that there might be a shock power transients from the main wave. We see there's a large scale current sheet forming, so you might get secondary X-ray emission, and everything very nicely carries over to the system. In terms of predictions that we can make. And you might ask, okay, maybe that's something we might expect to see at some point for like binaries, but is there any such system that would behave or have similar behavior from things that have already been seen? Maybe not for neutron stars in binary, but for neutron stars in isolation. And so the interesting thing is there was a recent detection of a very peculiar fast radio burst by FAST, which had about 11,000 bursts in less than a year. Think about that. The usual fast radio burst population normally has like either individual bursts, so they have some periodicity, but there's nothing that can give you 11,000 bursts, or better say, some of the episodes have 700 bursts per hour. And so the question then is, okay, if you have that, maybe that's associated with some cross selectivity. And people have put forward models for saying that maybe that's, can be explained with earthquakes on the magnetar in this case. And so the question then for us was, okay, this is great. This is an interesting detection in and of itself. And it, by the way, places strong constraints on the magnetospheric dynamics, because if you do something 11,000 times all over, you screw up your energy budget. And so maybe you constrain something. And so then what we said is, all right, we just do a full simulation. This is not a binary simulation. This is a sort of magnetar, magnetospheric simulation, where now we go after the same physics effect, but because this observation tells us we need proper modeling of the crust, we actually did a full magnetoelastic modeling of the crustal dynamics. So we really simulate how an earthquake of a neutron star look like, and then couple that to the magnetospheric dynamics, so you can see a lot of these waves. All these waves, by the way, form monster shocks. So you get exactly the same picture we've seen before, just many times over. You have nonlinear alpha waves. So everything I've shown you just in one source is in a big symphony. And you can use that to put constraints on the FRB emission mechanism because there's strong energetic constraints as well as dynamical constraints for which of these channels remain viable if you actually have a realistic sort of event like an earthquake on a magnet. You can ask me about that later if you're interested, but it's to show you everything that we do really has implications for other fields as well. So the final thing I want to do in the talk is basically say, okay, so we've seen that we can do all of this nice modeling for neutron stars, but looking ahead in terms of gravitational wave science, there are more sources that are interesting. For example, two merging galactic cores. And so the question is, can we make predictions of those things as well using the same tools or maybe even better tools than what we've used in the past? And the interesting thing is that all the picture I was telling you about the merger carries over in the same way. So if I make the same kind of cartoonish picture here, you can basically say, okay, maybe there's some initial galaxy merger or some dynamics that happen on effectively intermediate galactic scales. Here we already zoomed in quite a bit, but I'll show you kind of a zoom out later on. This is of 5 parsecs. Then at some point, the binary has to harden, ideally under the interaction of gas, stars, or dark matter, depending on what scale you're on. And then ultimately, when that collides, maybe there's a multi-messenger signature, much like we've been looking for neutron star mergers. And there have been interesting questions that have been asked recently in terms of if you take all of that, gas in that case, and you compress it down to, let's say, parsec scale, you might end up with what's called hypermagnetized disks. There's a big question about how quasar disks that you see in some of the cosmological simulations, say the ones done by my colleague Phil Hopkins, what they look like if they're magnetically supported rather than thermally supported. And then you can ask questions of like, if you actually have some of that, dynamics of those magnetic fields, do they change the inspiral? Do they change how black holes merge or whether they can merge? What does that tell us about the stochastic gravitational wave background? What does it tell us about transients? We can even do the same kind of modeling. Or we can ask, okay, if they launch jets, can these jets interact? Or finally, if the black hole gets ejected from the system after merger, can you get some transients from the recoil as well? And you can see from those images, you can use all of the technology that we have and make robust predictions, a robust understanding for how that works. And I want to give you some flavor of it. The main motivation is that, in 10 years, LISA will launch, meaning we'll have the ability to have space-based gravitational wave detections for black holes with masses 10 to the 5, 10 to the 6 solar masses. In the meantime, we got confirmation that there might be, tentatively, a gravitational wave background for merging galaxies 10 to 8, 10 to 9 solar mass black holes. The question is, under which conditions do those black holes evolve if they come from a realistic galaxy mergers? And if so, what does that tell us about potential electromagnetic transients or follow-ups? For example, for the pulsar timing array sources, there's 2 sources that are being searched for. And at Caltech, we have observer groups that use the radio facilities, the 40-meter dish that we have to look for radio emission that's periodic. Recently, there was a paper out just last week about sinusoidal variations with a harmonic, a 2-to-1 harmonic that might come from motion. So there's an interesting question for how much our models can actually help understand what you see or expect to be seen. And so to give you some idea of what we can do these days, using basically the advent of exascale computing, that's a simulation where we wanted to go to intermediate galactic scale. So the box is bigger than what I'm showing here. The box is roughly, somewhere over there on campus. It has an outer scale of 30 kiloparsec. And then we're able, using this massive, amount of GPU compute time, which is a lot, to zoom in all the way down to sort of a parsec scale and ask what is actually the accretion, the circumbinary disk look like? How does it affect the torques on the system? How does it affect outflows that are being magnetically driven? And we can even push that to 130 orbits, which for regular numerical relativity simulation, it's not numerical relativity simulation, but for the context of what we do for waveform modeling is really, really long. Usually those simulations have like 20 to 30 orbits.
Bit lost here. M87.
That's right. That's for an M87.
It's nearly entirely stellar. The amount of gas and thus the center. Are you doing stellar dynamics to bring?
No, we're not in this toy model. So we're not yet. It's a good question. So we're not yet doing stellar dynamics. So basically, just assuming that you have gas supply from like large scales.
Oh, okay.
What we will do,
that's not M87, what you just said.
Well, I mean, what we're doing is we're using an M87 like a dark matter background. So we're using gravitational background,
which doesn't matter for anything in the center.
Sure, it does. Well, it does matter. I mean, the cooling physics matters. Which is M87-like because it tells you whether you form a truncated disk at parsec scale or not. So basically, there's a cooling instability, meaning that the gas is coming in is actually forming.
Sure, but M87 doesn't have that.
Well, I mean, some models that have been put forward for M87, I don't think actually you can zoom in that far. well, I don't know, we can talk about it, but some models that have been put forward for M87 use exactly those kind of models that you form a truncated parsec scale disk. We can talk about that. What is interesting is, however, and I agree with you there, what we want to do next, this was just kind of the toy model that we wanted to do, is to actually get that directly from a cosmological galaxy merger simulation, because then we get all the interaction of dynamical friction, we get the dark matter.
I mean, I could point to systems, where gas is important, but for scale you're talking about, which is giant ellipticals, that's completely different stories.
Yeah. I mean, that's just, again, this is just a toy model that we're doing. I'm not saying that M87 has a binary or that it evolves in this way. I'm just saying that we needed to start somewhere, and that what we will do next is to actually do realistic merger conditions from galaxy mergers themselves. And then, we can look at the whole variability. We can look at the radiative conditions, the thermodynamic chemistry conditions, and so on. So that's something that's coming up. We just needed to, do a toy model problem to see if we even have the technology to do that, which is very, very challenging at the moment, or basically has been impossible before those new machines came along. Okay. All right, so asking then, what are the things that one should, look out for? One of them is multi-phase gas. So one of the things is, because you have realistic ISM cooling physics in the system, then the question is, you have hot and cold phases, and what that means is you actually have to model really the chemistry. You cannot just do simplified treatments that people have been doing. And what we find is that the gas disk that you form is very, very strongly hypermagnetized in that sense. The question is, we don't really resolve the thermal scale height, so take that with a grain of salt, because that could all go away once the disk collapses down due to cooling. But it's something that tells us that maybe magnetic fields are important, maybe really the radiation chemistry physics are important as well. And so one thing that we were thinking, okay, if you have strong magnetic fields, maybe they can really change the way that the binary evolves in the gas. And we have very good analogy for that, actually, for simulations trying to model M87 star for EHT type sources, meaning that, if you look at polarization measurements there, the black hole ends up being very, very strongly magnetized, meaning you have an ordered magnetic field close to the black hole. What that implies later on is that you're going to form a saturated state. And so the thing that, at least is consistent both with the jet power that you see for M87, as well as with the strongly ordered field line topology that you see in the polarization images over there, that the field is likely what's called magnetically arrested, meaning that the magnetic field regulates, the magnetic field sort of regulates the accretion. It doesn't really, make it stop accreting, but it kind of makes it episodical. So people call the left state sane in the simulation community, and the other one mad. And then the question is, if you had something similar for the binary, maybe, given that you have these strong magnetic fields, that changes the picture as well. And there has been a lot of work, I think, also including here for the planetary context, in trying to understand how binary sources embedded in a gaseous disk actually, interact with the torque. Does it mean that things shrink? Does it mean that things expand? And there's been a huge amount of work that's been done in two-dimensional simulations, because normally you need thousands of orbits to get some converged torque calculation, then to make predictions for what that means. But the thing that those miss out on, and there have been actually very great work by Vasilis, so kind of these short orbit simulations by a student, Vikram Manikantan, but what they miss out on, if you have some nonlinear dynamics, such as the one on the upper right, where the magnetic field is so strong that it might change the dynamics of the circumbinary disk, then maybe just like in this EHT image, there's nonlinear effects that are at play. And so what we did is we used this massive computer simulation to actually show that a similar state to what we think happens for M87 star for a single black hole can also happen on the binary scales for a binary accreting black hole with very strong magnetic fields. In detail, what we found was that if the magnetic field is so strong that it starts piling up in this cavity, you can basically have very, very strong magnetic fields that are pushing outwards, expanding the cavity, really regulating how the matter is being accreted. That has many implications. It has implications, for example, for angular momentum transport. It's implications for electromagnetic counterparts at merger, if that state is maintained until then. And we made a prediction for potential near-infrared transients from reconnection as you go closer to merger. Also changes how jets are launched, but it really means that, if you have these high fidelity 3D models, they can change a lot in how your binary evolves. If you look at the detailed torque calculation, which is shown here, everything that's a pink means it's mediated by the magnetic field. They're really showing you that, most of the angular momentum transport in the system now becomes magnetic. And then the interesting finding was there's a prediction that this specific binary under just hydrodynamical torque should never shrink. It should never inspiral, rather it should outspiral. If you go into this magnetically arrested state, suddenly it starts shrinking. So that really tells you that the magnetic field, if you include that in meaningful ways, can change the way that you interpret certain systems, their fate, and their observability. We did a follow-up of that together with Sean Ressler at CEDA, looking at the jet physics as well. I won't say too much about that, but basically, if you are inside a strongly magnetized cavity, you can actually get predominant jet launching. Those jets can cross, they can interact, they can wrap around each other, they can dissipate energy through reconnection, and you can make predictions for non-thermal counterparts to merging supermassive black hole binaries this way, going all the way from sort of the outer galactic scales or intermediate galactic scales down to the merger itself. And then you can even ask what happens after the merger. We've been doing a little work on that as well, because if you have the collision of two black holes in general relativity, it doesn't matter how big the black holes are. It's a scale-free theory in that sense, meaning that if you have specifically misaligned systems, or if you have processing systems with misaligned spins, this is based on simulations from the Simulating Extreme Spacetimes collaboration, there will be a non-cancellation of gravitational wave emission, meaning you get a linear momentum after the merger and your black hole gets kicked out. You can kind of see this here at this point when the black hole should start to fly out. Okay, maybe the video is not, now it's what you kind of see now, it's going out, and then it will just speed up at some point. Okay, and then the question is if that interacts with the surrounding disk, that may tell you, on which time scale to expect radio transients, let's say from the jet, or whether even a jet can be sustained. And so what we did together with Yoon-Soo Kim was a graduate student at Caltech. We actually did two things. First, we put a black hole just in a wind tunnel, just to ask what would specifically happen in this case. So here at the center is the black hole, just like this car. The matter is sort of streaming in to mimic the accretion flow. And you can see you can get unstable jet formation. It's very, very transient, very variable, but you can always launch a jet. And so you would always expect there would be some potential emission from that. But still the accretion conditions here are sort of toy model idealized. And so what we did recently, we said, okay, maybe we can really ask the question what would happen in the jet as well. And then we can make more robust predictions for what the jet dynamics, lifetime, and evolution is, which is very important because, on the time scale of those merging binaries in LISA, we may have, the opportunity to follow them for several days to weeks. And so if we know what to look for, that would actually be very helpful to find them because they will be in a large volume with many potential dynamics. So you can see here the jet is very variable. You can see that there's some kind of incoming inflow on the left. And then the final picture I leave you with, what does it actually look like if they run into a real disk? So we again use our toolbox using actually a realistic condition where we did a merger inside the circumbinary disk. And you can see as the black hole enters that disk, you get jet launching. At some point, it might be quenched, it might be bent in very weird ways. And that depends very strongly on the speed that the black hole has, so the kick speed as it's going into the disk, whether that transition is ultimately from supersonic to subsonic, or whether it's going at an angle, or all the different things. And very soon we'll have a paper out, so I can tell you more about that. Where we have different kind of angles, we can make different predictions, and we can give you a very good fit of the lifetime as a function of kick speed, meaning we can make a prediction on what timescales we might be able to see a radio jet from the merger of two black holes in the gaseous disk, given sort of parameters from the gravitational wave signal. Okay, with that, I'll leave it here. I hope I could motivate a little bit that, there's exciting things one can do with fine gravity, plasma physics, nuclear physics, both for things we can do at the moment, for things that we have seen or things we hope to see, and then also looking forward for things that we hope to model as we move to the new age of space-based gravitational wave astrophysics and beyond. So with that, thank you very much. I'm happy to take more questions.
All right. Questions?
Thanks for the great talk. You had very briefly mentioned that we can probe dark matter physics with these compact object mergers. I'm curious what kind of particles and interactions have people considered able to put compact?
Yeah, so I mean, there's basically been a whole zoo. Maybe the most most cases you can do two things. You can either say, for example, in a neutron star, you have so much dark matter that 10% or 20% of its gravitational mass is provided by dark matter. I think forming that is very, very hard because the question is, how do you condense all of the dark matter inside the star? Things that people are thinking about at the moment, also for Core Lab supernova, which I think is a more interesting model. If you think in terms of axion production under conditions of dense matter, specifically what happens in a neutron star is there's a pion process, both in the neutron star and in the supernova. There's a pion process where the pion couples to the axion that has been shown if you had a galactic supernova that could give you a potentially detectable gamma ray burst, making some assumptions for how close it has to be. Like Ben Safdie has worked on many models there, and we also did simulations of pion production in neutron star mergers, which is interesting. And then there are other models as well, like for for the black hole binary system, I mean, there have been claims that maybe you can use PTA signals to potentially put constraints on the dark matter impact on the shrinking of the binary, but that's all tentative. I mean, I wouldn't read too much into that, specifically if the dark matter is self-interacting or not. There have been like isolated models, but yeah. Basically, you can come up with a model for anything you want to look for, but I think those things at least are interesting questions. Yeah.
Maybe time for one more question. We're over time.
Thanks for a great talk. I was wondering if you've considered in these binary math simulations what the impact of jet feedback might be, especially since like in these like geometry simulations of Bondi accretion, you can see that actively affecting how your cavity or your horizons get rested.
I think it probably depends on what the jet direction is. I mean, we've only seen in the simulations with Sean, we've only seen that sort of the jet points in the direction where the disk, I guess, would be if the binary is strongly precessing. If the spin is aligned, the thing will just go up. And then the hope would be that maybe there is a decoupling, but we don't know. Like, we haven't checked that yet. But my feeling would be it will strongly depend on the alignment. Like, if suddenly the jet blasts in the direction of your disk, you could basically have feedback like that. But maybe not as extreme as in the one case.
All right, with that, let's thank Elias again.